Hello community! Today we have the impossible video. And I know that I will fail today trying to present you this video, but let's give it a try. So here we have it, and we have here a beautiful new text, and it is about here a super intelligent AI agent actions. And you might say, my goodness, what crazy YouTuber is now talking here about super intelligent AI? And if we look closer, computer science, Stanford University, just 2 days ago. So I got interested in this study because I almost missed this study. And they talk about a topic that slowly understand how important it is. A crucial challenge here in artificial intelligence concerning the alignment of our super intelligent agents with the human interest. And you might say, what's this nonsense? Is this ethics or whatever? We don't care. We are in AI research. No, we explore new frontiers. And yeah, I know. Super intelligent agent means here in this context that we have our AI agents that are perfectly pre-trained, perfectly fine-tuned. We have a perfectly alignment with whatever alignment methodology you want. You have a perfect RAG system. You have a perfect system with tool callings and everything. Imagine if we would have all this, and let's call this here the super intelligent agent, where all the technology up to today is implemented. We are still facing a problem. And Stanford looked at this problem in a mathematical way. And therefore it makes it almost impossible to do this video. But you know me, I want to try at least. So let's have a look. We are talking here about decision making, so taking specific actions by our agent under complete uncertainty. So our super intelligent AI agent, I call her SAIA, it has this job of performing here our alignment with the human interests. And we're not going with human interest with an individual, no, we're going with human society. Hey, it should be a challenge in this video, no? So how we do this? Think about medical AI. Medical AI system cannot rely only here on its clinical data on a person for an alignment here because the patient values the comfort level and the goal for the treatment may require a direct personalized understanding. Like in a normal hospital, you have somebody coming up to you, questioning you, how you feel, what are your parameters, what is your history, tell me about your life, what happened today. And in America, they ask you the credit card or what insurance company you are with. But you see, you need a lot of personalized data. And you might say, well, I can put this into a computer system. Yeah, but it is more, Because this interaction with a human in this context now serves to address here one of the core challenges of AI system. Their actions and their decision-making should align with human values and human objectives. And if you think about here an American hospital, who is taking the decisions? More and more humans like to say, well, it was not my decision, but the AI took here on a rational level certain decisions. And now they say, hey, wait a minute. We have to align all those actions with the human values and the human objectives. And to ensure that these decisions here by SAIA are beneficial and also ethical, the AI system must now learn to align its actions that are now learned from its pre-training data and with reinforcement learning by human feedback and everything that we have. They must align its action now with human preferences and much more difficult with human expectations. Because the doctor you're going to see has some expectations about you. You have some expectations what's going to happen to you in the hospital. Maybe the administration of the hospital has some expectation how much they will spend on you. So how can we cope with this completely uncertain environment? Now, what's interesting is that regular human interaction allow here the normal AI systems to continuously refine the understanding of what human actions, what the humans actually want, help to prevent potentially dangerous behavior of our AI system. So we are talking about an AI system that continuously learns on each case what human standard, what human goals, what human behavior would be, and what are the expectations of humans. And then our
SAIA agent, superintelligent agent must choose now specific action that lead now to our rewards, but also understand which action align best with the human values, even if those actions may not appear optimal in terms of the reward alone. So now it gets really difficult, because normally it was just, hey, optimize the reward function, no? But this is not enough anymore. Because optimize the reward function, for some patient that would be a real short action by an AI. So therefore, we have to think about, if we have now this perfect AI system and we put them in operation in environments like an insurance company, at the police, at a hospital, at a medical environment, I don't know wherever you are, what you are thinking of, you just cannot optimize for cold-blooded logic. Because we as humans, we have values and we have human expectation. And if you are the patient going to the hospital, you also have expectation. And now somehow this AI system, we have to take care that the AI is able to understand this and not just optimize its actions on the reward function alone. Now, these human preferences, they're real complex to understand. I mean, even for me as another human, I have no idea what the other human wants from me sometimes. All these preferences are, of course, context dependent. And what you think is the context may be completely different, because the doctor may only be interested here in your insurance company or your credit card number. And it completely evolves over time. So human expectation can vary based on the cultural, the ethical, and the situational factors that you are in and the complete system is in. We talked about a medical AI. Interaction with patient help here this med AI system to navigate these nuanced preferences, ultimately leading what we want is a more personalized, more aligned recommendation by our AI system. And everybody tells us, AI will augment the humans. So great, perfect. So let's have here an AI ability that is taken into account here this personalization level. Because, maybe we already have it here, the perfect med AI analysis system. But what it is missing is here personalization. And you can't code this into the AI. Somehow, and this is not a challenge, we have to make the AI aware of this, and somehow we have to code new algorithms that the med AI is able to learn this. Think about the AI in autonomous vehicles. And you might think, hey, this is a straightforward optimization problem. No? Goal is simply to minimize the travel time. You have a destination A and you have an end destination B, and you have all the route optimization and you minimize the travel time. Well, it is not that easy. Remember here the presentation by Elon Musk on this robot taxi that was coming in with 5 miles per hour, very, very slowly traveling, very, very slowly. Imagine you have here an ambulance and you have an autonomous driving AI ambulance. It cannot move with 5 kilometers per hour because the feedback that the AI is receiving now through the passenger reaction is here in the background they are calling to the driver, hey, patient is bleeding, go faster. So what is this strategy, this balanced strategy that respects the human expectation? Where are the limits for the AI? And we can't code this into the AI system. Because do you want to be in an ambulance that has been coded by Elon Musk's ethical standard? What is this AI allowed to do driving the ambulance? Have they included all the critical factors? Have they trained it on all possible environmental situations the ambulance could encounter? So you see, we have to build an AI system that is able to learn over time. Now, there's a little problem, and you could say many real-world environments are partially observable and absolutely uncertain. So this here tells us here, there's no way we have it in the training data. Yeah, maybe 80%, maybe you achieve 85%, but you always have uncertainty and you always have that it's partially not there. So an AI system may lack here the complete information about its environment and expectation here by the humans. So what do? We have somehow to capture here complex, evolving human preferences that may not be explicitly programmed into the AI, neither in the pre-training data, nor in the fine-tuned data, nor in the reinforcement learning by human feedback, nothing at all. We have to go now the next step, and we have to do another level. We have to achieve another level of consciousness of the AI system, that it is aware of its environment, that it understands human expectation, humans that are working in the environment that the AI system is operating in, and choose the action that fit for this particular system. And that is, it has not all the information about it. So we have to ensure that our SAIA remains aligned with the long-term human goals, avoiding unintended outcomes. And you know what? This helps us build trust, the human trust in AI system, which is critical for some sensitive applications. So we always say, hey, the AI is just augmenting here the humans in their job. So let's do this, no? So the AI needs here in critical situations here, human guidance. Human guidance is in the IUC critical for some decision making by the AI system that is operating, for example. So we do have to have the human in the loop. And now let's have a look at this study. This is what I almost missed here. Aligning here our AI agents via information-directed sampling. Here we have our Superintelligent agents. And here we have some beautiful study by Stanford University Computer Science and here Stanford University. And they think about how we can go the next step in AI. Now, if you look at the study, you might find, and that's why I call it, this is an impossible video to do. This is not what I can communicate in a 20-minute video. You can sit down, enjoy a weekend, nice cup of coffee, nice cup of tea, wherever you are in the world, and take this weekend and try to read the study. But I want to show you how beautiful that we have to move on with AI, that there are so many other problems that we have to take care of. So let me give it a try. So they introduce here a theoretical model, and they go here with the Bandit alignment problem that they define as an extension to the classical multi-armed Bandit problem. And you know, what we are facing there now is to have a mathematical base here for some computation to write code is a trade-off between our old friend, the exploration and the exploitation. So our SAIA agent now faces here the cost for querying the human. And this must somehow be balanced between exploring the environment and exploring the human preferences, so learn new facts and learn new information, and exploiting here the already accumulated information and make its own decision. How we do this in mathematics? Well, we have a probabilistic model, no? So key elements like environment, actions, and human preferences are now modeled, let's say this, in a probabilistically structured beta Bernoulli distribution. So this gives us here a kind of a handle to apply our mathematical knowledge to be able to solve this problem that we encounter. And then not only define the problem and say, hey, we have to look at this alignment of our AI super agent now, because how do AI integrate in our real human environments? And they say we need a better methodology. And they have a novel approach inspired by information theoretical principle, highly interesting chapter, please read this. And they call this the IDS, the information directed sampling, which is, of course, looking back at all the old models, and they say, well, we are better than Thompson sampling and all the other paradigm that we have. And this new approach, this new IDS, this information-directed sampling shows a more effective behavior in minimizing regret, especially when we have an AI system that is doing here a long-term horizon action. So it is not just optimizing for the immediate action, but it is optimizing here for a long-term goal to learn human values. And it is, of course, as everything in mathematics and theoretical physics, more or less an optimization problem. So we are here minimizing the regret function. Now, how can you think about transferring here an operative AI system in a medical AI, in an ICU, to a mathematical model that we have a minimizing regret function? This is kind of a beauty where you see mathematics and physics come into place. But of course, we have to think about the boundary conditions. So the AI agent or our SAIA agent does not start with the full knowledge of the environment or the full knowledge of human preferences, because each human that comes in has its own preferences. So it has to build, we have to start here with more or less an empty model and then build up a realistic scenario. So both the environment actions, so the actions by SAIA in a defined environment, and all the human query actions are finite, so we can solve it mathematically in a theoretical analysis. And this new IDS method is now based on the premise that an alignment problem benefits from reward-sensitive exploration. And this is now in a stark contrast to purely information-seeking exploration approaches. So we have now, and I have this here in green, I will stick to green here with reward-sensitive explorations throughout the presentation, that you see this is the new part that they are going to focus. Because it is not like in the old AI system, you just need more information, you just need more rack system to have more external information from a database or for a knowledge graph. No, we are saturated with information. We have all the information that we want that is available in the world. But now we have to go the next step. We have, based on the information, to decide on action that define reward functions in the real world, respecting the environment, respecting the human values, and respecting, of course, the job that is to be done as an AI system. And therefore, we do not need more information, but now we look at reward-sensitive exploration. So let me explain the methodology in my words, in my simple words, and I will fail. I know this. I can't give you the complete information, but I have to try. So formulated with a structure where the querying human, so the AI comes to the humans and say, hey, what is your feedback? What do you want? What are your preferences? All of this we say incur some costs, whatever the costs are. And those interactions here with the human yield rewards in the long term, based both on the environment outcome and the human preferences. And they use here the Bandit arms theoretical problem with rewards linked here, as I showed you, to the beta Bernoulli distribution. And this enables us now some complex reward structures. Because up until now we had those simple, silly reward structure, maybe linear. But now we have to go now to a more complex reward structure if we're going to talk about dynamic human expectations. So both explored and exploit and the Thompson sampling methodologies are now assessed by the team in Stanford, and they show that all of these classical methodologies fail, and they fail due to the linear regret accumulation. So they have here the complex reward structure, but the mathematical model is simply too simple. And you say, hey, hello! So the new IDS algorithm minimizes now the regret, and we will talk about in a minute what is now the specific regret function by combining the reward sensitivity and the information gain into its decision-making process, which action to take, selecting from all these probabilities now a specific action that yields both the learning about the preferences and the reward accumulation. Now, you might ask, okay, do we have a formula for IDS for the regret of an agent pi? Of course. As you see, if we see this now in this slide, we have now transformed this into a mathematical optimization problem. We just have to minimize here specific regret functions. Is this the perfect solution? No, of course not. But it is a beginning. Because up until now, what we're doing with our AI system is quite simple. No? We have a new AI model. We have a new vision language model. We can do some things. We have maybe a video generation model. But what we fail completely is to integrate those AI systems now really into the human world, into our environments, where we really need now the power of AI to augment us in our decision making, and therefore an AI has to understand our human preferences. Okay, so we have a mathematical optimization problem. Now let me skip the mathematical path and let's come right to the primary finding of the study by Stanford. This new IDS methodology achieves now a sublinear regret in both the action space and the time horizon. And this is what we wanted to achieve, because this is that the traditional methods fail. So this now implies that the IDS is better suited here for environments requiring both an extensive learning by SAIA on its environment, what is happening here in my environment, and a reward sensitivity. And remember, it is not about the immediate reward of an action, but we go here for a long-term optimization that aligns with human values. So this sublinear regret function that we're going to have a look at shows that IDS remains effective even if the interaction time grows. If we take one action, two actions, n actions, meaning now that SAIA continues to learn without unbounded cost. We have to be able to compute it, and we have to have limited costs. And when we say now that our IDS system achieves a sublinear regret, we mean that the IDS allows here our SAIA agent to learn efficiently from its action over time without the cost of an unbounded cumulative missed rewards. And this unbounded cumulative missed rewards function is what we call a regret in simple terms. Afterward, we regret that we had not taken some action that would have provided us with some rewards. Think about it in this simplified way. So you see, we are operating in a system that is dynamic, that has a high level of uncertainty, and we have a mathematical optimization problem in this system. How is it possible? Well, mathematics. So, IDS balances here our exploration. This means learning about the environment. Hey, where am I? What is my job to do? How can I interact with the environment? And learning about the human preferences. What is expected by the humans that I help them? How can I augment humans with my abilities? And the exploitation. This means maximizing the reward based on what the SAIA agent knows already, in a way that the agent's regret grows slower than the total time spent interacting with the environment. And here you have the core of the mathematical idea, how to do a system optimization. So, just to make it really clear, we're not talking about AI optimizing for the next immediate task. We are optimizing now an AI system interacting in its environment, in a medical system, in a financial situation, in a I don't know what situation, and we have a long-term goal. We want to align all our actions and all our future action by the AI with the human values, with the human expectation. And it is not only that an individual coder writes here some code and then all the autonomous vehicles on the streets of the United States of America behave in absolute the same identical way. We want to have an AI that learns interacting with the environment and learn what the human values are of the particular driver, of that particular car. Okay, great. So, significant takeaway is the insight that exploration must be guided by reward expectation rather than pure information gain to remain aligned over an extended time horizon. So this is here now where we break with the classical AI. This is where we take here the next step. I don't want to optimize a classical AI system here. I don't want to have some fine-tuning or some data compression or whatever. Now we integrate AI in human environments and we have human expectation. We have to build up human trust in those AI systems. And those actions that are taken by the AI, by our SAIA agent, they must now fall into this expectation, into those values, you might call also in ethics and everything else. How can we code this? How can we do here a self-learning system that would respect this? We don't have anything right now. And it all comes down here to the sublinear regret property. And this is really critical for extending here the learning and the reward accumulation, because it simply applies that as the agent learns more, it gets closer to its optimal performance and it suffers less from the missed rewards that I just talked about compared to a baseline optimal strategy. So we are not anymore in a system that is determined simply by its boundary condition where we know the dynamics. No. We are now out in the uncertainty of the real world. How we do this? Now, we have to start with a mathematical idea. We have to start with a mathematical methodology that we know of. No? We can't start from zero. So they at Stanford University decided to go here with a multi-armed Bandit problem. This is a classical model in decision theory and machine learning, and it is exactly focused here on our point of exploration versus exploitation. So this represents now a scenario where a decision maker, and this is SAIA, our superintelligent agent, must repeatedly choose from a set of actions, and now we make it simple. They are just multi-armed bandits, so these actions are now called the arms, like the levers on a slot machine. And this action is the simplest action. Huh? You pull down the lever or you don't. Couldn't be any simpler action. And we want to maximize the cumulative reward over time. And in this simple mathematical scenario, we can learn a lot about the dynamics of the system. So each action has an unknown probabilistic reward distribution. So each agent has to learn which actions are the best while it plays multiple armed bandit systems here in the casino. Yeah, let's take this example of a casino. We have several slot machines, and each slot machine have a different but unknown payout rate. So, of course, you as a human, you want to maximize the total money you win over a set number of plays. So if you keep playing only with one machine, you might miss out on better payouts from the other slot machines in the casino. But if you try each one machine too frequently, you might waste your time on the lower paying machine and you do not focus on the high paying machine. And you see, this is exactly the balance that we are looking for. Trying out new machines to find better payouts, this is our exploration phase, and sticking with those machines that seems to pay out here the most amount of money, this exploitation. And this exactly is, if you want, in a nutshell, what defines here our multi-armed bandit system. Now, in technical terms, it's a little bit different. Our arms, our actions, and each machine or each arm here has a different probability distribution of a reward function. Otherwise, it would be too easy, no? So, in a map within n arms, the agent has n choices at each time step. So each time the agent chooses now an arm, it receives a reward which is drawn from the arm's probability distribution. And this can vary significantly. So the reward distribution of each arm is unknown to the agent at the beginning of our experiment. And the goal is simple, no? The agent aims to maximize the total reward over a sequence of choices, typically over a finite time horizon. So let's do this. Now let's reformulate this for my green grasshoppers. So at the start, the agent, our SAIA agent, has no knowledge about the reward distribution of any of those slot machines. So we have to start. So it may begin by trying each arm a few times to gather some initial data about the performance and the payout ratio of each machine. And then our SAIA agent chooses here an arm according to its specific strategy. And this choice now influenced by the agent's current estimates of each arm expected reward. So you see, we have now a mathematical function that will calculate the expected reward based on the current estimate of each arm. So we have a limited knowledge and we want to project into uncertainty. And you say, hey, now it gets interesting. So after pulling the chosen arm, the agent observes now the real reward it receives and therefore updates its estimate for what is the actual arm's payout rate. So you see, the system starts to learn. Now the algorithm, then if we code this system, we have a lot of algorithms we know from mathematics. The epsilon greedy algorithm, or we go with an upper confidence bound algorithm, or we go with the classical Thompson sampling. However, the effectiveness of all these algorithms is often measured here as a regret function. And we know this regret. Now let's define what it means. Regret is the difference between the cumulative reward that would have been theoretically been obtained by always pulling the optimal arm in our casino example, and the difference to the cumulative reward actually obtained by the agent real-world choices. So it's rather easy to understand. No? The regret is just the difference what would have been theoretically the optimal solution minus what we really achieved with our actions, and therefore we learn how to optimize the action for the future. Now a lower regret indicates here a better balance between the exploration function and the exploitation function, as our SAIA agent effectively finds and exploits here the best arms, the best sequence. And now for the mathematical formulation of IDS, we can now have a look again at the new study by Stanford University, published October 18, 2024, aligning AI agents via information-directed sampling, IDS. So what they did, they said, hey, our new system should address the complex decision-making problems in which a SAIA agent must balance two goals: to maximize the rewards, we want them the highest amount of money, by exploiting our known information that we have, because we are in a real-world environment where we have now this information, this standard information, and then we want to explore to reduce uncertainty about the environment and the human preferences. So again, exploiting versus exploring, and we are back here to our classical system. Now you know, the IDS agent or SAIA can take actions on an environment. And this agent can now query also a human for the human preferences or for human feedback, although this will incur some costs. And as I told you, we are looking for the long-term learning. So the agent's goal, SAIA's goal, is now to maximize the long-term average reward by choosing particular action that balance here the learning about the environment, number one, understanding the human preferences in that particular situation, number two, and number three, exploiting current knowledge that the AI SAIA has to achieve the rewards. So you see, we have now an optimization problem where we have more or less three unknown functions. But we have the mathematical tools for this. We have the tools for this job. But just to explain what is the idea, again, long-term average reward, choose the specific action, balance the learning about the environment, understand the human preference, this is the new element if you want, and exploit here the current knowledge on the achieved rewards. You do all of this by deciding on actions. And because IDS focuses here on actions that balance here this information gain and the reward sensitivity, remember this is our new stuff, it therefore avoids wasteful exploration of low reward actions. If you want, this is another core sentence here. So instead, it explores here in a reward-sensitive manner, leading to accumulated knowledge that is directly relevant for maximizing here the overall reward function. If you want to code this, you have to have a mathematical formula. So this Stanford University group introduced here a concept called the information ratio. This is a measure that helps the agent decide here on the balance between exploration and exploitation for each action to be examined. So this information ratio I'm going to show you in a second is now here trying to balance the action that will, on the one side, improve the learning, thereby reducing the future regret function, and those that maximize the current rewards. Now, it's a rather easy, simple formula, yeah? However, notice that this information ratio for an action captures how much expected regret reduction in terms of a reward maximization can be achieved per unit of information gained about the unknown parameters. So you might have a smile on your face like I do have currently, and I think sometimes I'm just amazed what we come up with in probability theory in trying to model uncertain events. But if we go with this, so how we do this? So we select, SAIA now have our AI system now select actions by minimizing now the information ratio. So we do have here a beautiful function, and this is it. So if we do this for each time step t, we compute the information ratio for each possible action at a specific time step, and then we choose here specific action A for IDS that minimizes the information ratio. So this means the agent is selecting the action that offers the best balance of exploration and exploitation for that specific time step, maximizing thereby the reward sensitive or a new topic while maintaining here the alignment with the human preferences. So with this kind of simple mathematical formula, we can implement our new idea. And after selecting here the specific action, the AI agent SAIA now executes the action, the specific action chosen, and receives an outcome by the system or an observation from what happened in the environment after I've done this action. Seeing this, receiving here outcome, the system now updates its belief or its posterior distribution, if you want to go a little bit with more mathematics, about the unknown environment and the unknown human parameters based on the received outcome. And you see, this is now our self-learning methodology. And this update helps you to refine the future action selection, continuously improving the agent's ability, our SAIA ability, to achieve alignment with the human objectives over time. So we break all of this down to a mathematical optimization problem. So the agent needs here to learn the human preferences in a way that directly enhances its decision-making capabilities to align with the human goals. And don't get me wrong, I have nothing against ethics and some philosophical ideas, but when I say human goals, I mean immediate actions to be taken in a medical AI situation in an ICU or driving an ambulance vehicle. We are not talking about ethical constraints. They are in the background, but it is, hey, what's the maximum speed limit allowed? What is the criticality of the situation that I have to move those humans, those injured people here to the hospital? What are the parameters I can operate on? And if we have autonomous vehicles, this will be really important for our future. So, in this new AI alignment phase, simply acquiring more information is insufficient. This is the old AI. But now we have to move from information to reward functions, but in a much more complex uncertainty environment with unknown consequences that we have just to mathematically calculate. Okay. Short summary, IDS provides here a robust approach. Stanford University developed this for environments where the IDS agents or SAIA must operate over an indefinite or a very long time horizon with incomplete knowledge of both the human preferences and the environment. So our SAIA agent needs to keep learning about the human preferences over time, as both humans and the environments will change. So this is the reason why you can't have simple here reinforcement learning by human feedback, because it can change in the next minute. And the environment will change in the next minute. And you can have this predefined or pre-taken care of in the training data set. The AI has to learn in the real environment, in the situation that it encounters. And the AI has to know what are the right actions to take at specific times, given my information about the complete environmental parameters and given my information about the human condition and the criticality and the end. And this is a continuously self-learning, evolving AI system. And now you see, all of this is hidden in this beautiful study by Stanford University, and therefore I thought I have to show you this idea. And I know the complexity is so high that maybe I fail to communicate the beauty and the importance, but I have to give it a try. So therefore, here we are now. I hope you enjoyed it. I know I did not a good job, but it is a new idea what we have to do with our AI system if we bring them into our real human world, that they are really interactive. I'm not just talking about robotic system. Think about autonomous driving, ambulance system, medical AI assistance. Think about all these real world implementations. Our AI systems are not ready for this yet. I hope I provided some new information, and it would be great to see you in my next video.